Hi, my name is Eric Gonzalez, and today I'll be presenting our work, a model predictive control approach for reach redirection in VR. In VR, visual feedback of our hands is fully mediated through a display, and because vision is such a powerful sense, where we see our hands strongly influences where we feel that they are, and thus how we interact with the virtual world. Reach redirection is an interaction technique leveraging this fact that shifts visual feedback of the hand during reach in order to influence the user's hand trajectory. At a high level, this works because users correct for offsets by adjusting their real hand's trajectory to ensure their virtual hand reaches the virtual target. This has been used in a number of different applications, such as repurposing one real object to represent multiple virtual objects, and improving the ergonomics of interactions by optimizing target mappings. There have been a few different approaches to implementing redirection, but most are based on some form of spatial interpolation. For example, here the virtual hand in blue is shifted linearly to the left as the real hand approaches the target. This shift is directly tied to the real hand's position in space. This approach is appealing since it's so simple, but it doesn't easily adapt to changing environments or interaction uncertainties, nor does it consider how people reach from a sensorimotor perspective, which is something other fields have thoroughly explored. We see a need for a more flexible, generalizable, closed-loop approach to redirection. With this in mind, we propose a new Model Predictive Control, or MPC, approach to reach redirection. To introduce the basics of MPC, it's helpful to first consider a simple analogy. Consider the task of staying in your lane while driving. When you turn the steering wheel, you know how the car will respond. We can represent this relationship of input to output as a model capturing how the system changes over time. Using this model, you can predict how the car's trajectory might change based on different possible inputs to the steering wheel. With this ability to simulate future trajectories, you can then find the optimal action that gives you the best trajectory based on your goal. This is the main idea behind MPC. The case of MPC for reach redirection is surprisingly similar. In this case, we model how users reach to a target and use this to predict how different redirection offsets will steer the user's hand over the reach. The key here is that we use a sensorimotor model that captures the redirection process. As the user reaches to the virtual target, they continually adjust the position of their real hand to counteract the redirection offset and keep the virtual hand moving to the target. We can think of this series of offsets applied over time as the input to our model, letting us predict what the corresponding reach trajectory would be. Importantly, we can use this model to simulate reach trajectories for different redirection offsets. Based on a given objective, using our model, we can find the optimal sequence of redirection offsets. Examples of redirection objectives include having the real hand arrive at a desired target or following a desired path during the reach. MPC can also directly incorporate constraints, which can potentially capture things like avoiding obstacles during reach. We don't yet cover such constraints in our work, but mention them here to highlight the flexibility of an MPC approach to redirection. Importantly, this process is repeated throughout the reach. At each point in time, the offset between the real and virtual hand is recomputed by optimizing over a horizon of possible future trajectories. To recap, in contrast with interpolation methods, our MPC approach updates continuously, uses a generalizable framework that allows you to define redirection directly based on task goals and constraints, and is the first to leverage sensorimotor reach modeling to generate redirection offsets. Mathematically, the MPC process looks like this. At every time step, we solve a multi-step optimization problem constrained by the modeled reach dynamics and initialized by the current measured state of the hand. The objective is to minimize an overall cost associated with the redirection task. This process returns the optimal offset between the real and virtual hand, which we then apply before repeating this process every 10 milliseconds. I'll now briefly go over the two key components of this MPC approach, the redirection model and objective function. We start by considering the minimum jerk model, a well-known model of normal reach. This model suggests that users minimize the jerk of their hand's movement when reaching to a target, which results in a closed-form solution that depends on the total reach time. Previous researchers have shown how this solution can be formulated as an optimal feedback control law shown here. To capture the effects of redirection, we can modify the minimum jerk model with a biased sensory measurement, and assume that the state of the virtual hand is what's used by the user's internal motion controller. We can then build up a dynamic model for this modified system. Specifics can be found in our paper, but as a result, we get a linear, time-varying model for redirected reaching, where the redirection offset can be considered our control input. It's important to note, however, that this model still relies on a real-time estimate of overall reach time. Details on the validation of this model can be found in our paper, but overall it produces simulated trajectories that generally match experimental results. Moving on to the objective function, we break the objective into two costs. C-goal captures the goal of redirection and importantly can vary for different redirection tasks. C-warp captures the cost of warping the user's virtual hand from their real hand. The cost of warping considers three components: the magnitude of the applied offset, the change in offset to ensure smoothness, and the difference between the real and virtual hand velocities to further encourage agreement between real and virtual movement. As we mentioned, the goal costs can vary depending on what the desired goal of the redirection is. We explore two different redirection goals in this work, the first being endpoint-based redirection, which serves to guide the user's hand to a desired physical point. This cost penalizes deviations between the current offset and the desired endpoint offset as the hand approaches the target. Similarly, deviation from 0 is also penalized near the warp origin. The second redirection goal we look at is path-based redirection, where the goal is to guide the user's hand along a desired path as they reach to an object. Here we penalize deviation from desired real and virtual paths. Further details on the development of these redirection objectives and our MPC implementation can be found in our paper. We evaluated both endpoint and path-based MPC approaches against interpolation methods. More details can be found in our paper, but overall, our findings highlight the ability for MPC to generalize across different redirection use cases. These plots show the average offset applied by each redirection method as a function of reach progress. Our comparison of endpoint-based redirection showed MPC matched the performance of haptic retargeting, while our comparison of path-based techniques showed MPC tended to produce more variable and noticeable offsets than spatial interpolation. Future work should further explore path-based techniques and investigate the sources of these possible errors. Limitations of this approach include MPC's strong dependence on parameter selection and higher computation costs. Our model's requirement of reach time estimate is also not ideal since it introduces more potential sources of error. It also doesn't consider the arm's biomechanics or the role of other senses such as proprioception. Future work can incorporate more complex sensorimotor models and new formulations of objectives to build upon our initial results. Furthermore, in the future we aim to explore scenarios that better leverage the dynamic, closed-loop nature of MPC, such as redirected interactions in uncertain environments, reaching for moving targets, or avoiding dynamic obstacles in the real world. In conclusion, we believe that with its generalizability and flexibility, MPC is a promising step towards more effective, dynamic, and customizable redirection strategies. Thank you.